We've seen two methods for calculating the volume of solids of revolution. The disk method, when the cross-sections were circular, and the washer method, when the cross-sections had holes in them. Here we're going to learn a third method, which involves using cylinders to approximate volume. Some volumes are really hard to calculate using either the disk or washer method. If we try to rotate the graph of y equals 2x squared minus 2x cubed around the y-axis, we're going to find that we create a volume that's easier to solve with this new method of cylinders or shells than with either the disk or washer method. When we used the disk and washer method, we always chose a representative section that was perpendicular to our axis of rotation. Now we're going to imagine slicing our region into vertical strips that are parallel to our axis of rotation. When we revolve such a region about the axis, it's going to form a cylindrical shell. Like before, we're going to consider the area of the object that we've created with our rotation, but now we'll be looking at the surface area. We have to remember that the surface area of a cylinder is always given by the formula 2 pi r times h, where r is the radius of the cylinder and h is its height. The volume of a cylindrical shell then is going to be equal to its surface area times its width. So we get a formula for the volume of one cylindrical shell of 2 pi RH times W, where W now represents the width of that shell. If we then imagine dividing our solid up into a series of concentric shells, we can approximate its volume as the sum of the volumes of each of those individual cylindrical shells. In other words, we can write the volume as approximately the sum from I equals 1 to n of SA sub I times delta x sub I, where SA sub I is going to represent the surface area of the ith cylinder, and delta x sub I is going to represent the width of such a cylinder. Doing what we've done previously, we can then say that the volume becomes an integral. We let n go to infinity, and our volume becomes the integral from a to b of the surface area function times dx. Again, utilizing the fact that surface area is 2 pi times r of x times h of x, where r of x is a function that represents the radius of any given cylinder, and h of x is a function that represents the height of any given cylinder. We can establish a problem-solving strategy similar to the one we had for our slicing methods. We're going to choose our cylinder parallel to our axis of rotation. We're going to identify the cylinder's radius and height, generally by drawing a representative cylinder. We're going to express the surface area of that cylinder in terms of either x or y. We'll set up our integral with limits, and then we'll compute the integral to finally get the volume. Let's apply our strategy to see if we can calculate the volume that we create when we rotate the region in the first quadrant, bounded by the graph of 2x squared minus 2x cubed, around the y-axis. First, we need to choose our cylinder. We're going to choose it parallel to the y-axis, which is going to generate a cylinder similar to the one you can see in the animation. Now we need to identify formulas for the height and radius of that cylinder in order to come up with a formula for the surface area. So, like we did before, we'll go ahead and draw the two-dimensional picture. We've got the graph of y equals 2x squared minus 2x cubed. And there's a picture of our representative cylinder at some value c. We can see that the radius there is the distance between the cylinder and the x-axis, and the height is going to be the distance between the x-axis and the function. So now we can come up with a formula for the radius. The radius is simply just going to be the x value of our representative cylinder, and the height is going to be the function value, 2x squared minus 2x cubed. We'll use our formula for the surface area of a cylinder to get that the surface area of our representative cylinder is then given by 2 pi times x times 2x squared minus 2x cubed, which comes from 2 pi times r times h. Given our surface area function, which was 2 pi times x times 2x squared minus 2x cubed, we can now figure out our volume. Our volume is going to be the integral from a to b of our surface area as a function of x times dx. We need to figure out our values for a and b. These are going to be where 2x squared minus 2x cubed crosses the x-axis. So we set that equal to 0 and solve, and we get that x is 0 or x is 1. So our volume becomes the integral from 0 to 1 of 2 pi times x times 2x squared minus 2x cubed dx. Last step is to actually compute the integral. So we know that our volume is the integral from 0 to 1 of 2 pi times x times 2x squared minus 2x cubed dx. We'll move the 2 pi out front, deal with that constant later. So we have 2 pi times the integral from 0 to 1 of 2x cubed minus 2x to the fourth when we distribute the x on the inside. Taking antiderivatives, we get 2 pi times the quantity 1/2 of x to the fourth minus 2/5 of x to the fifth, evaluated from 0 to 1. Plugging in 1, we're going to get 2 pi times the quantity 1/2 minus 2/5. Plugging in 0 generates 0. So we simplify this to 2 pi times 5/10 minus 4/10. And we see that we get 2 pi over 10, which simplifies to pi over 5 cubic units for the area of this solid. Let's look this time at an example of rotating around the x-axis. We're going to take the curve y equals the square root of x and the line y equals 2 and revolve those around the x-axis. Once again, we'll choose a segment that is parallel to the axis of rotation and spin that around to create our representative cylinder. Now we need to figure out what the radius and height of that cylinder are. So we'll do the two-dimensional drawing again. We're going to graph our two functions, y equals square root of x, and the line y equals 2. We'll sketch in our cylinder again parallel to our axis of rotation, which in this case is the x-axis. And then we can see that our radius is going to be the distance that cylinder is above the x-axis. And the height of our cylinder is going to be given by the function y equals the square root of x. Because we're integrating with respect to y, since we're rotating around the x-axis in this case, our radius is going to be given by y. Our height, we have to solve our function or rewrite our function in terms of as a function of x. So we get x equals y squared, which makes the height of our given cylinder y squared. Putting that all together, our surface area is 2 pi times r times h, which will give us 2 pi times y squared. Now that we have our surface area, we're going to go ahead and figure out our limits and set up our volume integral. Our surface area, once again, was 2 pi times y squared, which of course is 2 pi times y cubed. Our volume must then be the integral from a to b of 2 pi y cubed dy. We need to figure out what a and b are. A and b are the lower and upper y values for our graph. We were given in the original instruction that the boundaries of this were the x-axis, y equals 0, and the line y equals 2. So those are going to serve as our a and b values. A will be 0, b will be 2. So now we know that our volume is the integral from 0 to 2 of 2 pi y cubed, and we can move that 2 pi out to the front before we integrate. Last, we go ahead and compute our integral. So our volume formula was 2 pi times the integral from 0 to 2 of y to the third dy. Taking an antiderivative with respect to y, we get 1/4 y to the fourth, evaluated from 0 to 2. So that gives us 2 pi times 1/4 times 16. When we plug in 2, plugging in 0, it gives us 0. So we end up with 8 pi cubic units as the volume of this solid. Let's compare the cylinder and washer methods by looking at a solid whose volume can be calculated either way. When we use the cylinder method, we're going to choose a cylinder that is parallel to our axis of rotation, the y-axis. When we use the washer method, we're going to choose a washer that is perpendicular to our axis of rotation. Regardless of the method, we need to figure out the formulas for the given quantities. So in both cases, we'll draw our two-dimensional picture. We've got y equals 4x and y equals x cubed. For our cylinder, again, we're going to draw parallel to our axis. We can see then that the radius of that cylinder is going to be its distance from the y-axis, and the height is going to be the difference between the two functions that our region is bounded by. In other words, our radius here is going to be given by x. Our height is going to be given by 4x minus x cubed. Surface area is always going to be 2 pi times r times h. So plugging in the formulas we just found, we get that our surface area for our cylinder is 2 pi times 4x minus x cubed, which we can simplify to 2 pi times 4x squared minus x to the fourth. For the washer method, we'll start with a similar diagram, drawing our functions in 2 dimensions. Y equals 4x and y equals x cubed. This time our representative washer is going to be perpendicular to the y-axis. We can see there that we have an outer radius that is related to our function y equals x cubed and an inner radius that is related to our function y equals 4x. However, for our washer method, we're going to be integrating with respect to y, so we're going to need to rewrite both of our functions as functions of x rather than functions of y. So, for our outer radius, y equals x cubed tells us that x is the cube root of y. For our inner radius, y equals 4x gives us that x is 1/4 of y. So now we know that our area of our washer is going to be pi times the outer radius squared minus pi times the inner radius squared. And that's going to give us pi times y to the 1/3 squared minus pi times 1/4 of y squared, which is pi times y to the 2/3 minus y squared over 16. We've got our surface areas, so now we'll go ahead and use those to set up our integrals for volume. For cylinders, the surface area was 2 pi times 4x squared minus x to the 4th. So our volume is going to be, as always, the integral from a to b of the surface area with respect to x. We need to find our boundaries for a and b. We're going to do that by setting the two functions equal to one another. So we get that 4x is equal to x cubed. Setting that equal to 0 and factoring gives us x times x squared minus 4 is 0. Factoring again yields that x must be 0, 2, or negative 2. However, we're limited to the first quadrant, so we're only going to choose x equals 2. So our final integral for our volume is the integral from 0 to 2. Moving the 2 pi to the outside, we get 4x squared minus x to the 4th dx. We'll do something similar for washers. We have a different surface area formula, of course, because we have a different slice. So our surface area here was pi times y to the 2/3 minus y squared over 16. Our volume then is the integral from a to b of the surface area, this time with respect to y. To find a and b, we're going to set our two functions equal to one another. Our functions were 1/4 y and the cube root of y. So we'll cube both sides of that to get 1/64 of y cubed is equal to y. Multiplying both sides by 64, we get y cubed equals 64y. Setting that equal to 0, y cubed minus 64y equals 0. Factoring out a y, we get y times y squared minus 64. That factors as y equals 0 or y equals plus or minus 8 are the solutions to that. We're only going to use 8 because, again, we're positive 8. We're in the first quadrant. So our volume is the integral from 0 to 8. Moving the pi to the outside, we have y to the 2/3 minus y squared over 16 dy. Our last step now is to compute our integrals to get volume. We'll start with cylinders again. Our volume was 2 pi times the integral from 0 to 2 of 4x squared minus x to the 4th dx. Taking antiderivatives, we get 2 pi times the quantity 4/3 x cubed minus 1/5 x to the 5th. And we'll evaluate that from 0 to 2. So we get 2 pi times 4/3 times 8 minus 1/5 times 32. Plugging in 0, both terms drop out. We get 2 pi times 32/3 minus 32/5. We get ourselves a common denominator so that we can combine those. That's 160 over 15 minus 96 over 15. So we have 2 pi times 64/15, which is 128 pi over 15 cubic units for our volume. Our volume for the washer method was pi times the integral from 0 to 8 of y to the 2/3 minus y squared over 16 dy. Taking antiderivatives there, we get pi times 3/5 y to the 5/3 minus y cubed over 48, evaluating that from 0 to 8. Plugging in 8, we get pi times 3/5 times 8 to the 5/3 minus 8 cubed over 48. Plugging in 0, again, both terms drop out. So we have pi times 96/5 minus 8 cubed over 48, which is 512 over 48. We need a common denominator again. The numbers are getting kind of big. We get 4,608 minus 2,560 over our common denominator of 240. And working that out, we see that our final answer is in fact pi times 128 over 15 cubic units, just like we got from the washer method. Now that we have several methods to compute the volume of solids of revolution, it's helpful to know which one to pick. It's important to remember that if you're using the disk or washer method, you're going to choose your representative disk or washer perpendicular to your axis of revolution. Shells, on the other hand, are going to be parallel to the axis of revolution. And your goal is to choose whichever one yields the simpler integral.